Now I am pleased to turn the webinar over to Ed Fenton, your IWCS moderator. Ed, please go ahead.
Thank you, Michelle. Our IWCS webinar series event is hosted by the International Cable and Connectivity Symposium. I am Ed Fenton, a cable industry advisor working with the IWCS team. As Michelle said, if you have any questions, please use the Q&A box on the bottom right of your screen to post a question anonymously. If you wish to contact the presenter or IWCS after the presentation, you will be given the contact points at the end of the webinar. Please note that IWCS does not distribute the presentation slides from either our conference session or these webinars. However, please feel free to contact the presenter directly and they will respond individually to you. Today, we welcome Dr. Earl Parsons, Principal Optical Engineer, CommScope in Texas, USA, who will be presenting his paper on bandwidth considerations for wavelength division multiplexing using multimode fiber. Dr. Earl Parsons received a BS in Electrical Engineering from Brigham Young University in Provo, Utah, in USA in 2006, and an MS and PhD in Optical Sciences from the University of Arizona, Tucson, Arizona, USA in 2008 and 2010. From 2010 to 2013, he was senior member of technical staff of TE Subcom, formerly known as Tyco Telecommunications. Since 2014, he has worked as the principal optical engineer at CommScope in Richardson, Texas, USA. His current interests are multimode and single-mode fiber optic systems. Dr. Parsons was a recipient of the IEEE Dallas Photonic Society Volunteer of the Year Award in 2017. Earl, we welcome you to present at today's IWCS webinar series event.
Well, thank you, Ed, for that introduction. I want to thank everyone for joining the webinar today. I also want to thank and recognize my colleagues at CommScope for their help in this work. So today I'm going to talk about multimode fiber. I'm going to talk about wavelength division multiplexing using multimode fiber. I'll emphasize which fiber parameters are most useful for predicting system performance when you have multiple wavelength channels, and also describe the difference between OM4 and OM5 fiber. When it comes to multimode fiber cabling, the three most relevant types are OM3, OM4, and OM5. These have all been standardized by the TIA, and you can see the relevant standards documents listed there. And each of these fibers have an EMB spec at 850 nanometers. And EMB stands for effective modal bandwidth, which is a measure of the data rate and reach that a multimode fiber can support. The EMB spec for OM3 fiber is 2,000 megahertz kilometers. And for both OM4 and OM5, it's a value of 4,700 megahertz kilometers. In addition, OM5 has an EMB spec at 953 nanometers with a value of 2470 megahertz kilometers. And having the two EMB specs allows OM5 to guarantee a modal bandwidth over a range of wavelengths. So if you're using applications like 100G SWDM4 that has a wavelength channel at 850, 880, 910, and 940 nanometers, or if you're using 100G BiDi, 400G BiDi, or 400G SR4.2, those have wavelength channels at 850 and 910, and all of those wavelength channels fit inside that OM5 bandwidth. It's between the 850 and 953 nanometer specs. So for all of these applications, if you're using OM3 fiber, the supported reach is 70 meters. It's 100 meters if you're using OM4, and 150 meters for OM5 fiber. And that long wavelength EMB spec at 953 nanometers, that's what allows OM5 to support longer reaches than OM4 for these applications that have multiple wavelengths. In addition, today I'm going to discuss a type of fiber I call OM4 Plus, and this is screened OM4. And I'd like to emphasize that the screening process has not been standardized, and the name hasn't been standardized either. OM4 Plus might be used by other people in the industry for different things, but I'll explain how it's defined in this talk. So what OM4 Plus is you take your population of OM4 fibers and you do what's called a differential mode delay, or a DMD measurement. And you look at that DMD data and you look at what the tilt of the fiber is. So I have a DMD sample at the bottom left part of this slide, where we have a series of output pulses from a multimode fiber under test, and they correspond to different probe positions. So what we're doing is we're taking a single mode fiber, scanning it across the end face of the multimode fiber, and for each place for that single mode fiber, we have a corresponding output pulse from the multimode fiber. And if we look at these pulses, they tilt up and towards the left. So this is a left tilt fiber. The pulses at the top of the graph are to have a peak to the left of the pulses at the bottom of the graph. And it's been proposed in the literature that these left tilt fibers can have advantages for transmission at 850 nanometers. That depends on launch conditions, of course. And these left tilt fibers also have a bandwidth peak at a longer wavelength. So I have EMB versus wavelength for 6 different OM4 Plus fibers. And you can see the EMB at 860 nanometers is higher than the EMB at 850 nanometers. So the thinking is these fibers could be useful for WDM transmission. So if we have a left tilt, then we have a higher bandwidth at longer wavelengths. And for SWDM4 and BiDi, the additional wavelength channels are at longer wavelengths. So these could be beneficial for those applications. Some people have gone so far to say that these OM4 Plus, or these left tilt OM4 fibers, will be just as good as an OM5 fiber for WDM transmission, and the results we'll show today demonstrate that that is not the case. The first experiment I'll describe, investigating OM5 and OM4 Plus fibers, is what I call the margin measurements. So we constructed and tested 24 different fiber channels using OM5 fiber and 24 using OM4 Plus fiber. These were double-linked channels with a total length of 250 meters, and each was constructed with a trunk cable that was 150 meters long, another trunk cable that was 100 meters long, concatenate together. We had some LC to MPO modules and some patch cords to connect everything. The 100G SWDM4 transceivers, which are commercially available, they were driven by a 100G Ethernet tester that had forward error correction, or FEC, enabled. And the FEC limit for SWDM4 is a BER of 5e to the minus 5. So if the total BER is below that, we should be able to correct all of the errors and have error-free transmission. So we used the 100G SWDM4 transceiver, and those are rated to support reaches of 100 meters if using OM4 fiber and 150 meters if you're using OM5. So we're going much further than the minimum supported distance for these transceivers. Finally, we had an attenuator right before the receiver, and that was to help us in the margin measurement. We would add additional attenuation to this path, and the highest amount of attenuation we could add without seeing those FEC errors or errors post-FEC, that was the margin available in the system. So here are the results for the 24 OM5 channels we constructed. And again, each channel is 250 meters long. And we have the margin. We have different symbols on this chart. There's different symbols to correspond with the 8 different transmitter-receiver combinations that we tested with each channel. We had a number of these 100G SWDM4 transceivers. We tested them with each fiber. And as you can see, there's variation in the margin channel to channel and transceiver to transceiver, and that's expected. The total performance of a link is going to depend on the interaction between the transmitter, its launch conditions, and the modal structure of the specific fiber. So that's expected. The lowest margin we measured was 5 dB, and we had the highest margin of 11.25 dB. So we were really excited to see these results because we're going 100 meters longer than the minimum supported distance, and we still have quite a bit of margin. Now, we did the same thing with the OM4 Plus fibers, but we don't have any data to plot because none of the 24 OM4 plus channels, again, this is our left tilt OM5, none of them had error-free performance at this 250 meters with any of the transceiver combinations that we had. So we could say they had no margin or they had a negative margin. And our suspicion was they didn't have the error-free performance because since they don't have a long wavelength EMB spec, then the bandwidth isn't high enough for the long wavelength channels. So to investigate that further, we took a closer look at 6 of the OM4 plus fibers and 12 of the OM5 fibers. We measured their EMB using a DMD measurement. We also looked at their tilt, and we looked at the BER performance. For the OM5 fibers, we verified that it met the TIA spec at both 850 and 953 nanometers. But for the OM4 plus fibers, we first made sure that they met the EMB spec for OM4 at 850 nanometers. We also made sure that they satisfied this special screening criteria. Now, of course, this screening criteria has not been standardized. It's proprietary, but we did our best to emulate that to verify that these are indeed OM4 plus fibers. We made sure they had a left tilt at 850 nanometers and that they had a bandwidth peak at a longer wavelength. And you can see in this chart that each of these OM4 plus fibers had a peak around 860 nanometers. Finally, we made sure that these fibers had an EMB below 2470 megahertz kilometers at 953 nanometers. That's below the OM5 spec. So the OM4 plus fibers are compliant to the OM4 standard. They meet the special screening criteria to be called OM4 plus, but they do not comply with the OM5 standard. To quantify the tilt of the different fibers, we came up with a parameter we call peak shift. So we have a DMD trace here on the right, and what we do is we select 2 probe positions. One is for the inner radius, one for the outer. In this case, I picked 5 microns and 19 microns. We look for the peak for those radial positions, and then we look at the difference in time between where those 2 peaks are located, and we call that peak shift. And we're subtracting the inner from the outer. So if we have a negative number for peak shift, that's going to correspond to a left tilt fiber. If peak shift is positive, that's going to be for a right tilt fiber. And the absolute value of peak shift corresponds to the strength of the tilt. So if you have a large negative number for peak shift, that's a strong left tilt. A large positive number would be a strong right tilt. And if these 2 pulses are aligned in time, they arrive at the end of the fiber at the same time, peak shift would be 0. That would imply low modal dispersion and high modal bandwidth. Now, I'd like to recognize that at the start that this peak shift parameter isn't going to capture all of the fiber information that's in a DMD measurement. Any tilt parameter is going to be limited. This peak shift is going to ignore some things going on in the DMD measurements. For example, if all of the pulses are broadened due to dispersion, then we're not going to capture that with peak shift. That won't be reflected in that value because we're just looking at the peaks of the different pulses. In addition, if there's any weird modal structure going on at the other probe positions that we're not looking at, then we're not going to capture that with peak shift. So this parameter admittedly has limited utility to predict the fiber performance, and we'll see that in the results. So the first question for peak shift is which probe positions should we select? We're going to look at 2 different pulses. Which 2 should we look at? It's from proposed in the literature that we look at the 5 and the 19 micron positions and compare those 2. And that makes sense because that's where we have in-circle flux requirements for transmitters for multimode fiber. So we'll look at that. We're also going to look at probe positions corresponding to the different DMD weights. So in the TIA standard, there's 10 different weighting functions for DMD measurements. I plotted those in the bottom left. And we're going to select an inner radius and outer radius position for each of those. The inner will be where this DMD weight function first crosses 10% of its peak, and the outer will be where it finally crosses 10% of its peak. So this is going to leave us with 11 different peak shift parameters. 1 through 10 correspond to DMD weights, 1 through 10, and then EF is the 5 and 19 microns. So the first thing we'll look at is how well does this peak shift parameter predict where the bandwidth peak is going to be for a multimode fiber. So again, if peak shift is 0, that means those two pulses are aligned in time. That should lead to that should indicate low modal dispersion and high modal bandwidth. And it turns out if a fiber has what I call a continuous tilt, this peak shift parameter works really well. So here's a DMD trace of a left tilt OM5. This is measured at 850 nanometers. And it's pretty clear from this trace that this is a left tilt fiber. Each pulse is slightly to the left of the pulse below it. So this is what I call a continuous tilt. So in this chart in the middle, I plot the peak shift parameter for the 11 different inner and outer radius parameters. And we see that each of them is linear, which matches what's been done by other researchers. And these have a slightly different slope depending on which inner and outer radius we pick. But we see that they all cross 0 more or less at the same point, around 880 nanometers. And if we plot that on top of the EMB measurement for this fiber, sure enough, the bandwidth peak is also around 880 nanometers. So we can measure this fiber at 850 nanometers, quantify its tilt with peak shift, and then use that to predict where the bandwidth peak of this fiber is going to be. And we can do that fairly accurately. Unfortunately, not all fibers are as pretty as the one on the previous slide. Many fibers have what I call an erratic tilt. So here I plot the peak position in time for the different radial positions for the 6 OM4 plus fibers and the 12 OM5 fibers. And we can see that whether these fibers are left tilt or right tilt, it really depends on which part of the curve you're looking. The probe positions kind of wander back and forth to the left and to the right. So this peak shift parameter isn't going to give us a lot of useful information. If we look at just the 5 and 19 micron probe positions that correspond to encircled flux, each of these OM4 plus fibers have a left tilt. 10 of the OM5 fibers have a left tilt, but 2 of them actually have a very slight right tilt. You really can't tell on the chart, but fiber 1 and 7 has a very slight right tilt. So when a fiber has an erratic tilt, it's very difficult for peak shift to reliably predict where the bandwidth peak is going to be. So on the top left, we have OM4 plus fiber number 4. We have the EMB in orange, and then the 11 different peak shift parameters. And the peak is at 860, and all these cross 0 near 860. So for this fiber, the peak shift works. It can help us predict where the bandwidth peak is going to be. For OM5 fiber number 6 there in the middle, some of these peak shift parameters cross 0 near the peak at 880, but some don't cross until 920 or 930 nanometers. So depending on where we're looking on the fiber, it determines how well we can determine where this bandwidth peak is going to be. And finally, OM4 plus fiber number 6 has a clear peak at 860 nanometers, but all of these peak shift parameters are 0 at 850 or shorter wavelengths. So none of them are useful for predicting the bandwidth peak. So our next question is, how well can this peak shift parameter correlate with the EMB that we can measure from our fibers? So we're going to compare the EMB measured at 850 nanometers to the peak shift measured at 850 nanometers. And for the rest of this talk, we'll look at the encircled flux condition, the 5 and 19 micron positions. So we're going to look at that for the 12 OM5 fibers, they're the green triangles in this graph, and the 6 OM4 plus fibers. And what we find is that when the EMB is really high, like above 8,000 megahertz kilometers, which is almost double the spec from TIA, it's sure enough, all the fibers that have that really high EMB have a small value for peak shift. It's close to 0. But not all the fibers that have a small value of peak shift or a small tilt have a high EMB. There's a couple of green triangles there in the bottom right. They have a small value of peak shift, so the pulses are nearly aligned in time, but their EMB is closer to fibers that have a large negative value of peak shift. And, of course, the large negative, that's a strong left tilt. So it's like saying all squares are rectangles, but not all rectangles are squares. The fibers with a very high EMB had a small peak shift or small tilt, but not all the fibers with a small tilt had a high EMB. So this is evidence that this peak shift parameter isn't capturing all of the information EMB captures. And really any tilt parameter is going to have a similar problem. So next we look at, can we measure the DMD and the tilt at 850 nanometers and extrapolate that to predict what the EMB at 953 nanometers is going to be? And it turns out that the answer is it depends. If you look to the top left of this chart, there is a trend where large negative values of peak shift correspond to high values of EMB. So again, peak shift measured at 850, and the EMB on this chart is from 953 nanometers. So the stronger left tilt you have at 850, that indicates you're going to have a higher value of EMB at 953 nanometers, but only to a point. As you go to the right on this chart, everything seems to level off. So I highlighted part of this chart from 2,000 to 3,000 megahertz kilometers. And if you focus on this chart, EMB is flat with peak shift. So it doesn't matter what the tilt is, we're getting about the same value for EMB in this region. This is an important region because the OM5 spec is 2470 megahertz kilometers. It's right in the middle of this box from top to bottom. So this box is the OM4 fibers that just barely missed the OM5 spec and the OM5 fibers that just barely passed that spec. And we really can't tell with precision what the EMB is going to be based on the tilt at 850. So this peak shift is an unreliable indicator. All right. So now I'll describe some additional measurements we do with these fibers where we look at their BER, and then we compare that to the tilt and the EMB of these fibers. So we take our same 100G Ethernet tester. This time we turn off the forward error correction. And this allows us to look at the BER of the 4 wavelength channels, 850, 880, 910, and 940 nanometers. This time the link was a single fiber, 250 meters long, and we tested these 12 OM5 and the 6 OM4 plus fibers. And we use the same transceiver for all the measurements so we can compare the performance between the two different types of fiber. Here are the BER versus receive channel or receive power for the 4 different wavelength channels. Again, 850, 880, 910, and 940 nanometers. The dark blue curve is back-to-back, so that's when we don't have a long length of fiber in the path. And we can see that all of these curves are well-behaved. They're all smooth. They all slope down. They all get below the FEC limit of 5e to the minus 5. And we don't see a lot of error floors. The only one we see is for the 940 nanometer channel, fiber 9, that's a purple graph. That seems to be developing a error floor, but it's going to be below 1e minus 7. So we can correct all of those errors and have error-free performance for all 4 wavelength channels using any of these 12 fibers. This works really well. And this corresponds to the data we had before where we had at least 5 dB margin for these fibers at 250 meters. Here is the same data, same measurements using the 6 OM4 plus fibers. The back-to-back is the same as the previous slide because we're using the same transmitter and receiver. And for the 850 and the 880 nanometer channel, things still work really well. They're well-behaved. For the 910 nanometer channel, we start to see some error floors with some of the fibers. And for the 940 nanometer, all the fibers have an error floor at or near or at or above the FEC limit of 5e minus 5. So due especially to that 940 nanometer channel, we can't have error-free performance for this system. I'd also like to point out we don't have data for the 910 and 940 nanometer channel using fiber number 2. That's because with that fiber, we just had sync loss at all received power. So it didn't matter how much power we fed the receiver. Due to dispersion, the signal was so degraded, we couldn't even measure how many errors there were. So we're going to take that BER data, and we're going to compare that to this peak shift parameter, to the fiber tilt. So here I have the BER of the 850 nanometer channel on the left and the BER of the 880 nanometer channel on the right. I'm going to plot both versus the peak shift at 850. So the thinking is, if we measure the DMD at 850 nanometers, that gives us the fiber tilt. Can we use that to predict the performance of these channels? And the answer is no. These results seem flat to me. Doesn't matter what the peak shift parameter is. If the fiber has a left tilt or no tilt or a right tilt, the BERs are about the same for both these channels. So I mentioned earlier, some people have postulated that a left tilt fiber will have superior performance than a right tilt fiber, even at 850 nanometers. And the thinking is there's what they call a modal chromatic dispersion interaction, where modal dispersion and chromatic dispersion can cancel each other out, which should improve the performance. Unfortunately, that relies on very specific launch conditions, and those launch conditions haven't been standardized, so you can't guarantee that you're going to get that with the transceiver that you use. So clearly with the transmitter we're using here, we don't have the right launch conditions for modal chromatic dispersion interaction. Otherwise, for both plots, the green triangles on the left of each chart would be a lot lower. They'd have better performance from that strong left tilt. And the green triangles on the right would be a lot higher because they would have a penalty from having a right tilt. Fortunately, everything's about the same, so we don't have that special launch condition. Oh. 1 second, everybody. All right, so now we're going to do the same thing with the 910 and 940 nanometer channels. 910's on the left, that's your longest wavelength if you're doing BiDi. 940's on the right, that's your longest wavelength for SWDM4. And again, we'll plot the BER versus the peak shift measured at 850. So you measure your tilt at 850, can use that predict your performance at the long wavelengths. And it turns out that if the fibers that had a very low BER, so they're in the bottom left of each of these charts, 1e minus 10 for 910, 1e minus 8 for 940, those fibers all had a strong left tilt. So yes, the fibers that had a very low BER had a very large left tilt, but not all the fibers that had a large left tilt had a low BER. There's a couple of blue squares in the middle of each chart. They have a strong left tilt, but their BER is a lot higher than what their tilt would imply. So again, all squares are rectangles, but not all rectangles are squares. In addition, there's two green triangles on the right of each chart. Those are the OM5 fibers that have a slight right tilt, and their BER is comparable to some of the left tilt, or even better than some of the left tilt fibers. So really, the tilt at 850 nanometers is an unreliable indicator of how well these long wavelength channels are going to perform. So what should we do instead? We should use EMB. EMB has been vetted by the industry, it's been standardized, and it's been used for a number of years, and it really captures all of the modal information of a multimode fiber. Here I plot the BER of the 910 nanometer channel and the 940 nanometer channel. Plot that versus the EMB measured at 953 nanometers. So how well do these results for the long wavelength channels correspond to the bandwidth measured at long wavelengths? It turns out there's a very clear relationship here. As you go to fibers with higher and higher values of EMB at long wavelengths, the BER of these long wavelength channels goes down. That means fewer errors. That means better quality signal, better performance. And since OM5 has a spec at 953 nanometers for EMB and OM4 does not, then OM5 is guaranteed to have a higher EMB than what you get with OM4 at 953 nanometers. So that's why all of the OM5 fibers that we tested outperform all of the OM4 plus fibers, these left to OM4 fibers that we tested. So really the best indicator of how well your long wavelength channels are going to perform is that long wavelength EMB. So in conclusion, we tested several OM5 and left tilt OM4 fibers, and the OM5 fibers outperformed the OM4. So we looked at this peak shift parameter. That can predict the bandwidth peak for a fiber that has a continuous tilt, But if a fiber has an erratic tilt, it doesn't work so well. In addition to this tilt parameter, it's an unreliable indicator of what the EMB is going to be at 850 or 953 nanometers. And you can't really use it to predict the BER of any of your wavelength channels if you're doing BiDi or SWDM4. So the EMB at 953 nanometers is really the best indicator of how well these long wavelength channels are going to perform. If you're interested more in this topic, I presented a paper about this in March at OFC, also at IWCS this past October. And then just last week, we had an invited paper published in the Journal of Lightwave Technology that goes over much of what I talked about today. Well, thank you for your attention. I'm happy to answer any questions you may have.
And thank you very much, Earl. So at this time, we will take as many questions as time permits, and I will start with this first question. Is effective model bandwidth EMB at 953 nanometers a better predictor than peak shift for performance at other wavelengths in addition to 910 and 940 nanometers?
Oh, that's a good question. So I show BER versus EMB for the 910 and the 940 nanometer channels, and I don't have it here what the 850 and 880 nanometer channels look like. That's in the papers, especially the Journal of Lightwave Technology paper. So what we see is the EMB at 953 is not going to really impact those two wavelength channels, 850 and 880, because they're far away. Really, the EMB at 850 nanometers is what you want to look at. And what we've seen is, yes, there is a dependence where as the EMB increases for 850 nanometers, you get better performance. Similar charts to what we have here, and that's been explored in the literature by other groups. The challenge, though, is when you have an OM4 or an OM5 fiber, the EMB is already really high. So instead of seeing this whole chart right here, if we were to plot it with these two fibers, you really see kind of like the right-hand side of this chart. So it's not as dramatic, again, because the EMB is really high. If we were to include OM3 fibers in this study and look at BER at 850 versus EMB at 850, then yeah, we'd see a chart more like this.
Okay, great. Thank you very much. Next question. Do you anticipate OM5 channel solutions, fibers, to begin replacing OM4 or OM4 Plus to achieve the sufficient bandwidth at longer wavelengths? And if so, when?
Oh, that's a good question. So really it comes down to cost and length, and it's going to depend on each end user to end user, what they need. So you've got to look at the links that you need in your, like if you're having a data center, what links do you need? If your links are short, then, and you use this BiDi or SWDM4, your OM3 or OM4 fiber might still work. You have to look at your losses and your reaches that you have. But if you need that extra reach, then you're going to need to go to OM5. So it really depends. I think it depends on if you want to upgrade your fiber, if that's a cheaper or lower cost solution for you, or if you're doing a greenfield deployment, the economics are different. So I think it depends on each end user, each customer, what they need. We're starting to see some deployments with OM5, and I think they'll start ramping in the next year or so.
Okay, great. Next question is, when will OM5 cable be available, and when will the corresponding components be available?
Oh, they are available right now. OM5 is available from several manufacturers, and the transceivers have been available, like 100G SWDM4 and 100G BiDi are both available now, from what I understand.
Okay, thank you. At this point, I'm seeing no further questions, so I wanted to thank you, Earl, for presenting this very interesting and important topic today. Please note the contact points being shown here should you wish to contact Earl after today's event. Each of these IWCS webinar series presentation events are recorded and will be archived on the IWCS.org website. It normally takes up to 2 weeks for these to be posted. The IWCS webinar series will conduct presentation events on a monthly basis. Webinar events will take place on the third Friday of each month at 10:30 a.m. Eastern USA time. Our next scheduled webinar event will be on Friday, January 18th at 10:30 a.m. Eastern USA time. Each of you will be receiving an announcement for the event a few weeks prior. Please feel free to share our announcements with your colleagues so that they can join in and register as well. For over 67 years, the IWCS International Cable and Connectivity Symposium has been the recognized leader showcasing new technologies in cable and connectivity products, processes, and applications. Our next annual international conference will take place on Sunday, September 29th through Wednesday, October 2nd, 2019, at the Charlotte Convention Center in Charlotte, North Carolina, USA. In addition, the third annual UL and IWCS China Cable and Connectivity Symposium will take place on Monday, March 25th through Wednesday, March 27th, 2019, at the Marriott Hotel City Center in Shanghai, China. Please visit our website at iwcs.org for more event details. In just a moment, you will see a brief survey so that you can provide us your feedback and comments on today's event so that we can further improve this webinar series for you. Thank you for participating, and this concludes today's event.